Dear colleagues of the ESA Forum, firstly, I would like to express my respect to the organizers of this ESA Forum Conference 2020 by converting it in these difficult days of the pandemic into the first virtual conference in history of the ESA Forum. This virtual conference is cleverly structured and managed. Congratulations and much success further on. Secondly, I would like to thank sincerely Professor Markus Bambach for inviting me to present this keynote. This keynote is about the results of a collaborative research center on damage-controlled metal forming processes funded by the Research Foundation of Germany, DFG. You see at the footnote the four research partner institutions as the University in Aachen, University in Dortmund, University in Cottbus, and the Max Planck Institute in Düsseldorf. And I have not listed all the 40 contributors of the center as co-authors. You will find a picture at the end of this presentation where almost all of them are present. I just name the authors as authors, those who supported me in the preparation of this presentation. Ladies and gentlemen, the topic of damage is a controversial and a difficult topic if you discuss it in the manufacturing community. Therefore, I would like to start firstly with our perception of damage and our vision. Let us look to a piece of metal which has the dimensions 50 millimeter to 100 millimeter, thickness 1.5 millimeters, and the material is DP800. If you investigate this metal under a scanning electron microscope, you will find about 85,000 voids. And you will find that the density of the voids is about 11 voids per millimeter cube. And this is, of course, just an average value. Now, the question is, what happens with those voids if you do metal forming? If you do, for instance, bending, air bending, how many voids will be generated in the forming zone? That's a question. And the strain which we generated in the experiment was 0.41. If you look to the forming zone, you will find that in the forming zone, which is a tiny zone, you have 27 million voids, which corresponds to roughly 390,000 voids per millimeter cube, just in the forming zone. This is 35,000 times more than you have in the initial starting point. So something happens here, and this is what we call the evolution of damage. And at that point, I would like to emphasize the difference between damage and failure. Failure is if we observe macroscopic cracks, and those cracks lead to the malfunctioning of the component, so the component is a failed component and cannot be used in service. This is what we understand by failure. However, if we look to damage, we start with a material which might have some voids in them, but which might have also some inhomogeneities that could be precipitations, inclusions, or even second phases. And as you start loading and plastically deforming, what you see is that voids, separation at those interfaces happen, and those grow with increasing plastic deformation. And at the end, those voids coalescence with the neighboring voids and decoalescence further until a macroscopic fracture occurs. So our concern is up to this red line. This is the part of the material we consider to be constituting a functional component, although you have voids in them, although they are coalescence, and although they are not in the initial state, this part is still a good part. And if you look to our example, we can find at the martensitic islands voids that grow with plastic deformation, as you see here, very impressively. At the end, our message is, our mission is, damage is not failure. So you might have damage in the part, Still, it's a good part, but we are not looking to a part which goes to failure. Failure is the final stage of the evolution of damage. So this brings us to a paradigm change in a way. If you look to the design process consists of getting input of the material properties, the function of the component, the load and service of the component, and then designing out of those the geometry of the component, and then manufacturing the component. Now, the properties after manufacturing are not usually the same as the properties you assume at the beginning. So therefore, you get a loss of a safety margin. You have a part with unknown safety margin. You can improve that if you use the product properties after manufacturing in the design process. Then your safety margin will be much better, and it will be a deterministic safety margin. So until now, the properties which are considered after manufacturing are strain hardening and residual stresses. Damage, which I showed you before, is not considered as, or basically not considered as damage. And that's what we would like to change in our research center. Now, the important message here is we would like to move from formability in forming, which looks for preventing cracks in forming, to usability, that means to produce good parts but with low damage value that have much better performance. Let's turn back to our first example with the banding. Now, if we use this air banding or replace this air banding process by a process where we can superpose pressure during the banding process in the deformation zone, for instance by an elastomer cushion, then we can see that we can reduce the voids from 27 million to 15 million during the forming process. It's the same product, the same geometry, the same material, but the voids are significantly less. They are about 45% less. And especially if you look to the density, which reduces from 390,000 to 210,000 voids per millimeter cube. Now, if you go even one step further and say, okay, what's the benefit of that? And then look to the performance of this airband part and the performance of this part, which is banded by superposed pressure and with less voids, you will find that for instance, the performance evaluation by the impact energy, that the impact energy of the airband part is around 0.8 joule per millimeter square, whereas if you introduce a moderate pressure, you can increase this energy to 0.9, and then if you increase the counter pressure, you can increase the energy even up to unity, 1 joule per millimeter square. And the benefit is quite obvious. You have an increase of 90% performance, you improve with that the safety margin, and at the same time you can, as an alternative, reduce the sheet thickness of the part. So this is our mission, this is our vision of damage in metal forming. The Collaborative Research Center, Transregio 188, has 3 fields of research within its body. It's the characterization field, the technology field, and the modeling field. In the technology field, we are basically concerned with the metal forming processes themselves, like air bending, extrusion, rolling, deep drawing, and similar processes. In the characterization area of research, we look to quantifying the damage level on microscopic level or by measuring densities and so on. At the same time, we look also to quantify the performance of the part in the characterization field. In the field of modeling, our aim is to predict the development, the evolution of damage during metal forming, but also predict the performance of damaged parts in service life. So this is the global view of the activities of our research center, and I would like to give you a little bit deeper some findings of what we have achieved in the last 3 years. Now, before I do that, let me introduce briefly the team, the research team. So we consist of four places in Germany. So in Dortmund we have different institutes which are working together, and in Aachen we have 5 institutes which are working together, then in Cottbus 1 institute and 1 department in the Max Planck Institute. So all together we are 18 PhDs. We have 19 leading researchers, so supervisors and senior researchers, and we have 14 industrial companies who support us in conducting the research and show us always the industrial relevance of our research and give us valuable guidelines. So the first funding period started 2017. We are almost at the end of this first funding period, and what I will present you today are some of the results and findings within the last 3 years. So let us come firstly to the manufacturing of semi-finished products, which goes through the hot rolling and cold rolling routes and heat treatments. So this is a typical forming route for sheet metals. We start with continuous casting, heating, hot rolling, cold rolling, heat treatment, and then the processes of banding, deep drawing, and so on start until we end up with the component and check its performance. So in the field of flat rolling, we analyzed in the first period of our research work how the voids which are inherently present after casting close during the rolling process. And what we found is that the type of the voids which we have after casting and their form, their direction, their orientation has an immense effect on the closure of those voids during the flat rolling process. Now, what you will see here at the top is a finite element modeling, and we just look to this element within a representative volume element. Here we considered a spherical void, and what you see here is the strain. And let us see what happens with this void during the formation. And you see at the center you have a closure of that void to a certain extent, and what you see in those graphs, let us just look to this graph, with the increasing strain we see different closure speeds of those voids depending on their geometry and depending on their orientation in the metal. So this was a very important finding for us. In a second investigation, we looked to the bulk forming route, and in the bulk forming route we considered the hot rolling within a caliber rolling process. So what we did is we were searching for the amount of damage depending on the design of the caliber rolling process. So we started with a rod which has 60 millimeters diameter and reduced it to the diameter of 40 millimeters, which was used then after in the cold forging process, and looked for different ways of designing the sequence of the calibers. Here you see different forms, and at the end the amount of void volume fraction in the part. So, depending on which route you select and which geometry of the rolling tools you select, you end up with different damage distribution in the part. The volume void fraction is relatively low after the process, after the rolling process, which is a good sign for the process itself. So, this was another important finding for us. Now, let me come to the component manufacturing. I would like to start with cold forging. The cold forging process is a very simple process and fundamental process in bulk forming, where you start with a billet and push the billet with a punch through a die opening in order to obtain the extrudate. The important parameter here, process parameter here, is the so-called extrusion strain, which is nothing else as the logarithm of the initial cross-section divided by the final cross-section A1. And interestingly, this strain is exactly the strain you get with local analysis at the center line of the extrudate. And this strain is constant over a certain radius here, so that we could take specimen out of this region and analyze them further. Another important parameter is the die angle, which is designated by 2 alpha, and I would like to show you now the experimental campaign which we have conducted. So on the left you see for a material 16 manganese chrome S5, which is a typical cold forging steel, we use different strains from 0.5 at the axis up to 1.5 logarithmic strains. So we are speaking here about very, very large logarithmic strains. And all of them for a constant die angle. And then, as an alternative, we produced a series of experiments with the same strain, that means with the same cross-sectional reduction, however, with different angles of the die. And now let me show some results. So what we found is, if we analyze the stress state and we are looking for the triaxiality, and the triaxiality is, as you know, the hydrostatic stress divided by the equivalent stress, so it's a measure of the hydrostatic stress, the first invariant in the stress tensor, we see that for the same cross-sectional reduction, that means for the same plastic strain we have at the center, we get for different angles different triaxialities. So with 90-degree angle, we get the maximum triaxiality in the deformation zone as positive, which is 0.2, and we get a triaxiality of minus 0.3 almost for the smaller die angle 30 degrees. This is very important. And now we look to those 3 specimens and found that the density for the one with the highest hydrostatic pressure is highest. That means the voids which we have in the specimen closed very effectively, or didn't open at least. And then for the case of 90-degree angle where we have a positive triaxiality, we get a reduction of the density, which indicates that we have here damage nucleated and growing during the deformation process. So this is a very important result. As a next step, we analyze now for those specimens the product performance, and for that purpose we use specimen out of the extrudate in the middle with almost uniform homogeneous material properties, and extract their fatigue test specimens. We extract Sharpie impact tests and we extract tensile test specimens to analyze the apparent Young's modulus. And those are the results. So this is a quite difficult or crowded figure, so please concentrate on, for instance, the impact energy. That's this one for 30 degrees. where we have a maximum triaxiality, which is shown here, of a negative value 0.9. For that, the impact energy is the highest, and the impact energy falls for the specimen with 90-degree angle for the same strain. So strain hardening is not the factor, residual stresses is not the factor, because you have almost no residual stresses in the core of the part after extracting the specimen. So at the end, we can show that the impact energy of this part improved with decreasing cone angle, improved with increasing triaxiality in the negative direction. So then you have the apparent Young's modulus. The apparent Young's modulus in the same way decreases with increasing cone angle from about 195 megapascal to down of 185 gigapascal. So there is an apparent decrease in the Young's modulus, which means you have a loss of stiffness with increasing damage at 2 alpha 90 degrees. And the same for the fatigue life, as you can see here. And that's the interesting summary. We have a void area change from 2 alpha 90 degrees to 2 alpha 30 degrees for the same strain of 75%. The number of cycles to failure in a fatigue test increased by 25% through that. The impact energy increased by 80%, and the apparent Young's modulus increased by 10%. So what we can show here is that the damage does affect component performance very clearly. I would like to show you another example as from our findings in the field of air bending. So we found that in air bending we cannot change the parameters like in extrusion by just playing with the bending parameters. The triaxiality doesn't change significantly. So we had to introduce another methodology, and that was to apply external pressure during the process. One very well-known procedure in industry is to use an elastic cushion for that purpose. But we found that this doesn't generate predictable pressure at one hand, and on the other hand, it does not generate high enough pressure for the process. So we invented a new process, new bending process, where you see here the details. So the dies are rotating. I will show you the slide in a minute. And if you look closely to the contact area, we produced here a pressure during the free bending action through that force on the lower die. And you see here the tool in action. So that's the sheet, and you produce the pressure by pushing that lower die, and in this way you end up with a pressure superposed bending process. And here are the results. If you do air bending and look to the voids area fraction starting from the tensile side of the bending area towards the compressive side, this is the distance from the outer fiber, you see that the area fraction is around 0.20% and decreases to 0.15, etc. in the inside. If we apply now our RS bending, where we reduce the triaxiality from 0.57 to 0.06 minus, we see that the void area fraction reduces significantly, almost by a factor of 2. And we can see that also in the density. If we take density specimens and measure the density, we see that the density of the RS bending part is higher. That means it's denser. That means the voids are less as compared to the air bending part where the density is lower. Now, reduced triaxiality leads to lower damage. And now, the next step, what is the performance of the part? And for that purpose, we look to an impact energy test. So we use special specimens in this form. This is the banded area and this is the notch, and the impacting test is conducted in this direction. And what we found is that for a steel of DP800, we have an increase in the normalized impact energy with an increase of pressure. Here you see the approximate pressure values. So Kf is the flow stress. If we apply a pressure which is 1/3 of the flow stress, then we have an increase in the impact energy by almost 0.12 joules per millimeter square. And if we increase the pressure to half of the flow stress, we can increase that even by 20%. So this is a very important finding and a very clear message for the future of the design of metal forming processes. Here is another example from the sheet metal forming part. Now, what we see here, this is from our colleagues from WZL in Aachen, the deep drawing process. So what we try to do here is we try to look to change the load path during the forming of a part that looks like that from the blank. So the blank is the same, the finished part is the same. What we change is we do it by one-step deep drawing, or we do it by a multiple step drawing. So first draw one cap, then redraw it, and then redraw it again and end up with the finished part, or redrawing by reverse deep drawing. So deep draw one cap, redraw it in a reverse sense, and then redraw it again to end up with the same cup. Our hypothesis is here that we change by that the load path, we change by that the triaxiality, and by that the damage level in the part. Here are the results. Now, just consider this right figure. This is the single-step deep drawing process, the multiple-step forward process, and the reverse multiple-step deep drawing process. What we see on these figures is the damage distribution, and you see that the multi-step process brings damage at a different location as the two other ones. So this is the maximum damage in the wall at this point. However, if you use the reverse one, you get the maximum damage at another position in the wall, and if you use the single step process, you get the maximum damage at another position, and more important, in the transition part where you have critical loadings of the part, you see that the single step process delivers the worst damage compared to the two others. So by that we could also prove our vision that we can change the product property damage in the part by changing the path of the loading. Now, in the next slides, I would like to show you some results about our modeling and characterization. So, one important finding in our research center in the first period was that the material property identification is an important issue. We found, for instance, if we use the classical strategy for the damage models to identify the process parameters by the loss displacement curve or plus some strain values, you end up with damage values which are not in accordance with our experimentally measured damage values. So we change our strategy. We call that the micro predictions or process identification, product parameter identification property. This the strategy A, where we use the damage evolution and the load displacement curves to identify different parameters, for instance here in the Gerson model, and used those for the prediction, compared to the strategy B, which is the classical one, where we use only macroscopic values. And here you see the procedure. So this is the parameter identification of the plasticity part of our model, where we identified the plasticity parameters, and this is the parameter identification strategy using the void fraction or the equivalent strain, identifying the void evolution parameters in a Gerson model. The results are shown here. So if we consider the banding process with a macro parameter identification method, which is the classical one, and with the micro one, you get completely different void fraction distributions. As you can see here, the factor difference is 35. Here is the distance from the outer radius, so we start at this point and go inside and measure the void fraction. If we use the macro parameter identification strategy, we get values, so please notice the coordinate system is cut at this point, so you have a jump here to values of 7%. If we measure them, we measure values of 0.2%. So there is a difference, a huge difference between the macroscopic parameter identification with the same model, with the same Gerson model, just depending on how you determine your parameters of the model. And if we do it with our micro parameter identification procedure, we get not exactly the same as the experiment, but at least the order of magnitude is very similar to the experimental ones. So in the next slide, I would like to show you some interesting findings, how we try to identify the mechanisms of damage which we use to feed our models and design our models accordingly. So one example is here about the decohesion mechanism of martensite. So how do voids occur? You see here some voids. How do they occur by the decohesion of the martensite from the matrix? So for that purpose, we look to the voids as shown here, different voids, and then analyze how those voids get larger and increase their size. So there are two modes, mode 1 and mode 2. And those two modes are important for our models. So what we did was we analyzed those modes under the microscope and found that the uniaxial tension one corresponding during the uniaxial loading, we found that this mode 1 direction, which corresponds to 90 degrees, this is the cracking angle, is the basic mode which we have in the cracking of the martensite. Oh, sorry, here is the angle once more shown. And that is the preferred orientation for cracking in uniaxial tension is the 90-degree mode. If you look to equiaxial tension, the situation changes. Then any angle, any orientation can be a cracking orientation. So that's very important that we have to identify those mechanisms in order to use them in our models. Another example. What is the fracture toughness of a martensitic island? For that purpose, we look to a martensitic island under the microscope and then use the FIP technology to prepare a test specimen and then load that test specimen. I have to show you the video here. You see, we isolate the martensitic island, prepare the specimen, and then initiate a crack here, and then use bending tests, intermittent bending tests, to observe the crack propagation during that process and found out of this the J integral, which is important, and also the stress intensity factor, which we can derive out of that for the martensitic islands. Now, this is an average one because depending on the composition of the martensite, you get different values, and what we determined here is for the batch of different values, an average initiation, the stress concentration factor, and a stress concentration factor of a strain of 0.02. So this is a very fundamental research which we can use directly in our models. Another important thing is to determine the plasticity properties, the plastic properties of our material. And for that purpose, we used again some micro pillar compression tests and found the slip lines, and an interesting result is, if you look to literature, you expect the 110 slip plane with the 111 slip direction as the typical slip system, but what we found is dislocation activity on all theoretical slip systems is involved in the plastic deformation of this material. So one very important result. With those, we went also to develop our macroscopic and multi-scale models. Will give you an example for the macroscopic models. This is a model which is a gradient enhanced damage model, which has, beside the elastic and the plastic contributions, also a contribution for the gradient damage model. And our model has a very special property that all the parameters, the plasticity and the damage, are decoupled, so you can have a multi-surface analysis and determine in a very flexible way, or reflect in a very flexible way, the properties of that model. So this model is, as I said, a non-local model, and you see here for the bending case the effectiveness of this model. You see on one side a classical damage model. In that case, it was a Lemaitre model, where we have, depending on the mesh size, different damage values. And here you see the gradient enhanced damage model, and on the bottom the fine mesh, on the top the coarse mesh, and you have exactly the same damage distribution for that model. So a final example from the computational side before I end my talk is related to the low cycle fatigue. So our models for low cycle fatigue are shown here, and what we see here is in case of low cycle fatigue, our simulation and our modeling is both supplying an excellent comparison and predicting the effect of damage on the low cycle fatigue. So with that, I'm coming to the summary and to the important points. What are the industrial utilization of our work? First of all, the process design can be influenced. We have shown that you can change the process design by introducing additional pressure. I haven't shown you the rod extrusion experiments, but also here, by imposing counter pressure, you can change the residuals, the damage state, and hence increase the performance of the part. We have shown that you can change the process design. For instance, in deep drawing, instead of conventional deep drawing, you can do redrawing and end up with a different damage distribution and hence different performance. What I haven't shown you as well is you can improve the microstructure during the heat treatment and during the rolling, such that the microstructure is convenient to reduce the damage evolution in the process. Those are important findings. Another important finding for the industry is understanding the physics. We understood that we can change the damage evolution by the process parameters, and damage evolution is not only a function of strain, it's a function also and especially on the stress state. So for small strains and large stresses, we get different product properties. Although the strains are larger, the damage in the larger part is lower. I haven't shown you that, but that's one important result which we found in various works. So, depending on the evolution, damage evolution, we get different product performances, and those damage evolutions depend on the stress state. That's an important physical insight. And the key messages I can give you at the end is ductile damage is a component property. Damage during metal forming can be controlled by process parameters and process design. Damage influences the component performance significantly, as shown in this example with counterpressure and no counterpressure here. And with that, I would like to thank you for your attention and your interest. And I'm very happy to answer your questions and receive your comments on that work. Thank you very much, and have a good time and remain healthy, and all my best wishes. Thank you very much.